This is Pete Waller, and this is the hydraulics section of Chapter 6. And it's necessary to make sure that pipes are large enough to carry the flow to the end of the irrigation system without excessive pressure loss. And one of the worst feelings is to glue a pipe network together, turn the water on, and realize the pipe system is too small to carry the required flow rate. Such as I had one student, and actually he was an engineering student, put in a pipe system. I think it was several hundred feet long, and he told me that he wasn't getting any water out of the end. And it turned out that he didn't make the proper calculation to see if the pipe would carry the water. And so he had to dig up his pipe, and it was really embarrassing for me that a former student could not even calculate how big a pipe he needed. I was depressed, actually, and I'm sure he was embarrassed. So what I'd like you to do is pay attention so that this never happens to you or me again. One difficulty most people have with talking about irrigation is that water pressure is often talked about in terms of head, and people use terms such as feet or meters in order to express the pressure. And this section will help you understand that concept. So pressure is a form of energy, and pressure is the amount of force per unit area exerted on the walls of a vessel or pipe. And the way we can think about it is that 1 cubic foot container of water contains 62.4 pounds of water. So what is the pressure at the bottom of the container in pounds per square foot? So we can draw the container, and there's 62.4 pounds in the container, and the bottom area is 1 foot squared. So if we want to know how many pounds per square foot we have, we can divide 62.4 pounds divided by 1 square foot, and so the answer is 62.4 pounds per square foot. The next question is, what is the pressure at the bottom of the container in pounds per square inch? Well, in a square foot, we have 144 square inches. So we take 62.4 pounds divided by 144 square inches, and that equals 0.433 pounds per inch squared, which also equals 0.433 psi. Psi is pounds per square inch. So the pressure at the bottom of the container in psi is 0.433. Then we can ask, what is the pressure in the container at a depth of 0.5 feet below the top of the container? Well, we have half the number of pounds, 31.2. So if we divided 31.2 by 144, we'd have 0.215 psi. So the relationship between feet and psi is that 2.31 feet is the same as 1 psi, and 1 foot is the same as 0.433 psi. So atmospheric pressure, you could say it's 34 feet, you could say it's 14.7 psi, or you could say it's 1 atmosphere. So let's look at an example where we convert from feet of pressure, or from psi of pressure to feet of pressure. So what is the feet of pressure when the pressure is 2 psi? Well, we take 2 psi and we multiply times 2.31, and so that's the same as 4.6 feet. Okay, what is the feet of pressure when the pressure is 50 psi? Or we could say feet of head. Well, we have 50 psi times 2.31 equals equals 115 feet. So it's very simple to convert from PSI to feet. The next example, we'll calculate the pressure in units of feet at the bottom of the container from exercise 6-1. So the one way we could do it is we could just look at the depth. The depth in the container is 1 foot, so the pressure at the bottom of the container in head is 1 foot. So that's easy. The other way we could do it is we calculated that the pressure in PSI was 0.433 PSI. We could multiply that times 2.31, and that equals 1 foot. So our next example is we'll calculate the pressure in PSI in feet ahead at the bottom of a swimming pool that is 9 feet deep. So the pressure in head or feet would be 9 feet at the bottom of the swimming pool. Then we could take the 9 feet and we could either divide by 2.31 or multiply by 0.433. We'll multiply times 0.433, and our answer is about 4 psi. I don't know the exact answer there, but we could multiply that out. There are two types of pressure in pipe systems: static pressure and dynamic pressure. Static pressure is the pressure when the water is not moving. So it would just be due to the depth, say in the bottom of a pool would be static pressure. But dynamic pressure is less because the water is moving through the pipe and losing energy. But first we're going to look at the static pressure in a pipe system. So example 6-5 says write down the static pressure in PSI in feet of head at each of the fittings in figure 6-7. So here's the figure 6-7, and we have points A, B, C, D, E, and F. And so the water level is here, and then the pipe inlet is 20 feet below the water level, and then C and D are 55 feet below A and B, and then E and F are 16 feet below C and D. So we don't have to worry about any water flowing. This valve is closed, and all we have is static pressure. So all we have to worry about is the depth of the water below the water surface right here. So the static pressure at A and B are going to be 20 feet. So we can just write static pressure is 20 feet at A and B. And then C and D are 75 feet below the water surface. So we can just write 75 feet for the pressure at C and D. It doesn't matter that the water had to go sideways. All that matters is the vertical depth below the water surface. And then the static pressure would be 75 plus 16, or 91 feet below the water surface at points E and F. Okay, now what we need to do is we need to convert the pressure in feet to pressure in PSI. So once we've calculated the pressure in feet, we can convert to PSI by multiplying times 0.433. So the PSI at A and B would be 8.66. The PSI at C and D would be 75 times 0.433, or 32.47. And the PSI at E and F would be 91 times 0.433, or 39.39. We also could have done 91 divided by 2.31 and had the same answer, 39.39. So we can either multiply times 0.433 to get PSI, or we can divide by 2.31 and we get the same answer. As I stated before, dynamic pressure is the pressure that you measure when water is flowing through the pipe, and that is different than static pressure because energy is lost as water flows down the pipe. So the dynamic pressure is going to be less than the static pressure. And just in case you are interested, the energy is lost because molecules are sliding past each other, creating friction and losing heat energy, and that energy loss results in a lower pressure. So there's been many equations and tables that have been developed to calculate the amount of energy loss in a pipe. And in this class, we're going to use friction loss tables. And those are given in Table 6-4, 6-5, and 6-6. These are the tables that would be in irrigation handbooks or catalogs. So here is a typical friction loss table, and it's very easy to use. All you do is you go down the left side and you look for your flow rate. So let's say your flow rate is 10 gallons per minute. And then you can look for the friction loss in feet per 100 feet. So for example, the friction loss in 1-inch pipe would be 2.9 feet per 100 feet of pipe. So if you had 10 gallons per minute flow rate, you would lose 2.9 feet for every 100 feet of pipe. This means that if you had 200 feet of pipe, you would lose 5.8 feet of pressure. But if you use larger pipe, then you would lose less pressure. So in this way, you can see that all you have to do is go down to your flow rate, see how much pressure you lose in feet per 100 feet, and then multiply that times the length of the pipe. So let's look at an example of how to calculate pressure loss in a pipe. So we have 200 feet of 1.5 inch class 160 pipe, and the class refers to the wall thickness. For instance, in Table 6-5, we have class 200 pipe. In Table 6-4, we had class 160 pipe. So this is the table that we're going to use in this example. So if we look at 25 gallons per minute in 1.5 inch pipe, and we go to our table, here's 25 gallons a minute, the very last row, and 1.5 inch pipe is the third column. So we can see that we have 2.442 feet per 100 feet of friction loss in 1.5 inch pipe for 25 gallons per minute. So the friction loss is 2.442 feet per 100 feet. Our pipe is 200 feet long, so we have 2.442 feet per 100 feet times 200 feet equals 4.884 feet, or about 5 feet of friction loss in that 200-foot length of pipe. So the dynamic pressure is calculated step by step, and you always use this equation in this format to calculate it. So we have point 1 and point 2, where the water is flowing from 1 to 2. So we already know the pressure at point 1, so we want to calculate the pressure at point 2. So the pressure at point 2 would be the pressure at 1 plus the elevation gain minus the friction loss. Let's say that the friction loss from 1 to 2 is 1 foot. That means that our pressure, and then let's say that the pressure at 1 was 50 feet. That means that our pressure at 2 would be the pressure at 1, 50, plus the elevation gain. Well, it's a level pipe, so there's no elevation gain, minus the friction loss, which would be 1 foot. So the answer would be 49 feet. The pressure at 2 would be 49 feet. All right, so this problem is why they sometimes call irrigation irritation instead of irrigation, because this will really irritate you. What we're going to do now is we're going to calculate the dynamic pressure in the pipe system where we calculated the static pressure. So what we need to do is go step by step, and the way we do that is we start at our known pressure and we just work our way down the pipe from point to point. With the static pressure, it didn't really matter where we start. We could calculate the depth below the water level. But now we're going to have to start at the beginning and go step by step and calculate the pressure at each point. So we'll start with point A. And fortunately, we know the pressure at point A because it's 20 feet below the water level. So even though water is flowing in the pipe, it doesn't matter that water would be moving downward in this tank because there's so little friction loss we can neglect it. So we can start at A and assume that the pressure is 20 feet. And then we can see that the distance from A to B is 13 feet. It wasn't 8-1, it was 6-3. But remember that friction loss in the pipe was 2.44 feet per 100 feet. We already established that the pressure at A was 20 feet, and the length of the pipe is 13 feet. So we can calculate the friction loss from A to B as 13 feet times 2.44 feet per 100 feet equals 0.32 feet. So the pressure at point B is the pressure at A plus the elevation gain minus the friction losses. This is always the equation you use when you go from point A to point B. So the pressure at B would be 20, the pressure at A, plus 0, because there's no elevation gain between the two, minus 0.32 feet equals 19.68 feet. The next step in example 6-4 is to calculate the pressure at point C. So now we know the pressure at B, and we're going to calculate the pressure at C. And so there's a 55-foot elevation gain. So if C is lower than B, then that would be called an elevation gain. So the pressure at B was 19.68 feet. And now we're going to calculate first the friction loss between B and C. So we have 55-foot pipe length times 2.44 feet per 100 feet, or 1.34 feet. So the elevation gain is 55 feet. So now our pressure at C would be our pressure at B plus the elevation gain minus the friction loss. Well, our pressure at B was 19.68. Our elevation gain is 55 feet. Our friction loss is 1.34 feet. So our pressure at point C is 73.34 feet. Our last exercise in this section is to redo example 6-4 and to calculate the friction loss and the dynamic pressure for class 160 pipe at 22 gallons per minute. We're going to use 2-inch pipe. So if we put the table here and we go to 2-inch pipe, which is the fourth column, and we go to 22 gallons per minute, we can see our first column ended because this pipe is not large enough to carry that flow. The velocity is too high. But we go over fourth columns, and we can see that our pressure loss for 22 gallons per minute is 0.6493 feet per 100 feet. Let's just write that down. 0.6493 feet per 100 feet. So we know that our pressure at A is 20 feet. And next we'll calculate our pressure at B. So we can just say that our pressure at B is our pressure at A, 20 feet. And remember, there's no elevation gain between A and B. So our elevation gain is 0. 20 feet plus 0 feet minus 13 feet times 0.649 feet per 100 feet. And so the answer would be 19.92 feet. So that would be the pressure at B. Pressure at C would be 19.92 feet plus 55 feet, because remember C is 55 feet below B. And then we could subtract our friction loss, which would be 55 feet times 0.649 over 100, which would equal 74.56 feet. Then we just go step by step. Now we look at D, and we can see that D is at the same elevation as C. So D would be 74.56 feet plus 0 feet minus the distance, which is 16 feet, times 0.649 over 100. So let's just do a sample calculation for this pressure loss here. So we have 16 feet times 0.649 divided by 100 equals 0.10. So now we have 74.56 feet plus 0 feet minus 0.1 feet is 74.46 feet. So now we start at point E with start at point D with 74.46 feet. And let's get our bearings back together here. Remember that D now is 74.46, and we're trying to calculate E. And E is 16 feet below D. So now we have 74.46 feet plus our elevation gain, 16 feet, minus 16 feet times 0.649 over 100 equals 88.13 feet. Okay, and finally we can end with our calculation for our valve pressure at F. F is our discharge valve pressure, and so that's 12 feet from E. So we can start with 88.13 feet at E plus 0 feet because there's no elevation gain minus 12 feet times 0.649 divided by 100 equals 87.79